Hello everyone, today we're going to be talking about atomic structure, basically the history of the atom. And we want to make sure we understand how that all looks inside, and so let's begin. So the first thing we want to talk about is a little timeline. And it all starts out from the context of a guy named Democritus and Leucippus. These guys are Greek philosophers. And Democritus actually coined the first philosophical thought of what is the smallest possible particle. So if you were to try and crush maybe some M&Ms or something, how small can you possibly crush it? Or in his case, I think he was thinking about a piece of rock. How small can you crush a rock? And so the Greek word atomos kind of relates to the idea of the smallest possible particle, and that's where we get the word atom from. So it's from his philosophical talk that then later, that was 400 BC, 2,000 years of alchemy, which is basically trying to create gold out of anything, because gold was so valuable back then. So you had all these guys using chemical technique to try and create gold. Little did they know that was really not very possible. We'll talk about why that's impossible in a little bit later. And then when we get into the 1500s, we get to some ideas of systematic metallurgy, how to then create and fold metal to actually create very strong, metals that we use for swords and for armor, etc., etc. And we find some medicinal applications of minerals, but it wasn't until actually back in the 1600s when a guy named Robert Boyle started doing what is called quantitative experimentation, which we're starting to do in the lab, where we actually collect data, masses, volumes, and using all those to help identify elements. And again, another 100 years later, George Stahl talked about phlogiston theory. I'll let you look that one up. And later on, Joseph Priestley discovers oxygen. All of these discoveries, along with Antoine Lavoisier, and he talked about his role of oxygen, or talked about the role of oxygen in combustion, law of conservation of mass. And so Antoine Lavoisier was, based on all the experiments he used to do, was the first one to actually kind of discover this concept of the law of conservation of mass when we talk about chemical reactions. Further down into the 1800s, and so now we're getting to more recent history, a guy named Joseph Proust, law of definite proportion, when we talk about the creation of compounds. John Dalton came up with an atomic theory. So it wasn't until actually in the 1800s we started talking about the atomic theory. Gay-Lussac talked about gases and the volumes and how that actually affects them. Avogadro came up with the idea of what the volume is for a mole of gas. Berzelius talked about relative atomic masses, modern symbols for the elements. Mendeleev actually came up with the first periodic table organization, finding patterns in the elements, which we'll talk about in more detail later. J.J. Thomson came in with his discovery of the electron. Becquerel discovered radioactivity. And in 1900s, we get the charge and mass of the electron, the existence of the nucleus and its relative size. Sustained nuclear fission was in the early 1900s, and of course that leads into nuclear reactors and nuclear bombs. Lawrence then discovered the cyclotron and transuranium elements, and were able to create those actually using the cyclotron. So that's basically the basic history and timeline. A lot of the stuff that we discovered happened in the last 200 years, and that's actually pretty impressive when we talk about the history of science. It's, once you start learning stuff, that acceleration of knowledge just rapidly develops. Just the idea of the transistor and how it started out to be just some circuit that we used to make now encompasses what makes up all the iPads and cell phones, etc., etc. Technology accelerates the more you know. And so, just in highlighting some of the important stuff. Back in 1808, Dalton came up with an atomic theory. And his atomic theory basically contains 5 parts. All matter is composed of extremely small particles called atoms. So using a Tomos word, the Democritus, when we talk about anything, paper, pens, water, all of these contain atoms as long as it's considered matter, not empty space. The second thing is, atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. So you read that now and you say, that makes sense. I mean, if you have a different element, you should have a different size and mass and property. Gold is not the same as silver. Water molecule, actually let's talk elements first, sorry. A hydrogen molecule and an oxygen molecule are totally different. One's flammable, one makes things burn more. And so those are, of course, things that he talked about back then. Atoms cannot be subdivided, created, or destroyed. So if you have an atom, you cannot subdivide it, create it, or destroy. Atoms of different elements combine in simple whole number ratios to form chemical compounds. So if you ever form a compound like water, then you know you're going to combine into whole number ratios. There's always 2 hydrogens for every oxygen. If you have sugar in your, in this, there's always 6 carbons to 12 hydrogens to 6 oxygens for the sugar, for the glucose that's actually in here. And so these ratios, of course, exist, and it was through all this experimentation that we're able to figure these out. And in chemical reactions, atoms are combined, separated, or rearranged. So these are his ideas back in 1808. Later on, we'll talk about how some of these ideas are actually not so true anymore because of what we know about the atom. And we'll talk about those details later. Alright, so concept check. Here's a question. Which of the following statements regarding Dalton's atomic theory are still believed to be true? Elements are made of tiny particles called atoms. All atoms of a given element are identical. A given compound always has the same relative number and types of atoms, or atoms are indestructible. So as it turns out, the first one that is still believed to be true, all atoms of a given element are identical. And, whoa, what happened here? A given compound has the same relative number and types of atoms. So it's supposed to highlight number 3, not number 4 there, so I apologize. And those two are still true. The idea that atoms are indestructible, that's not so true anymore. And elements are made of tiny particles called atoms. Well, oh wait, these things actually got shifted. I'm actually supposed to highlight 1 and 3. What's actually not true anymore is number 2. All atoms of a given element are identical. It turns out there's isotopes out there that a carbon atom can have. Carbon 6, carbon 12, carbon 13, carbon 14, and so they're actually not identical. And atoms are not indestructible because when we deal with nuclear reaction, we actually change an atom and break it into pieces. Or if I take 2 of them, I can actually fuse them together. And we'll talk about that in more detail later. So, several changes have been made to Dalton's theory. So here's the points that I wanted to make. Atoms of a given element are identical. That's not true anymore. Atoms of an element have a characteristic average mass, which is unique to that element. So carbon would be 12.011 because there's a carbon 12, a carbon 13, and a carbon 14. And we'll show you in a little bit how when you calculate it, the average turns out to be 12.011 because most of them are carbon 12. Atomic theory number 2, atoms cannot be subdivided, created, or destroyed. Well, that's not true anymore either. We can actually, they cannot be subdivided, created, or destroyed in ordinary chemical reactions. However, these can occur in nuclear reactions. And so those are the 2, of course, that we wanted to make sure we understand have changed. In the discovery of the electron, I'm going to actually do this demo in class. J.J. Thomson used a cathode ray tube to deduce the presence of a negatively charged particle. And of course, he used a positive plate, which you can see up here, and a negative plate, which is down here. And when he shot that beam of electrons, it was attracted to the positive plate, which meant that whatever was on here was a negatively charged particle. And so he was actually the first to recognize the presence of this negatively charged particle, and was able to then detect the existence of the electron. And from a bunch of his experiments, he was able to figure out the mass-to-charge ratio of the electron. Thomson's atomic model, because of all the work that he did, he believed that electrons were like plums embedded in a positively charged pudding. Thus it was called the plum pudding model. And so the picture of it looks like this. He knew that those electrons should be able to fly around. And so, since it had to come from somewhere, he believed it came from the atom itself. So he was the first to start thinking about the structure inside the atom, and he thought that the positive pudding was also mixed with these negative electron charge, the the plums itself, and of course these were able to escape whenever you put them through high voltage. And again, we'll talk about that in more detail in class. That leads us to another idea, is that the mass of electrons. So once J.J. Thomson was able to figure out the mass-to-charge ratio, Robert Millikan was able to actually determine the mass of the electron itself. And what he did was he created a scenario where he was able to take oil, charge them, and then create this plate structure in here, a viewing microscope, and these electrically charged plates was able to create a scenario where the electrons just kind of stood there and floated in midair. Okay, actually not electrons, but the oil drops were able to float because the charge on them would be attracted to the positive plate and would also be repelled by the negative plate. And by doing that and knowing the mass of those drops, he was able to do some physics calculations. So if you ever take AP Physics B, we actually do this problem in the class and figure out how the force necessary to make it float, and they're able to figure out the charge of the electron based on the data that J.J. Thomson got for the charge-mass ratio. He was able to figure out the mass of the electron. So once you knew the charge, then you could figure out the mass. So that was the hard part, and he figured out the charge, which then allowed us to figure out the mass. And so then the mass of the electron turned out to be really, really small, 9.109 times 10 to the negative 31 kilograms. And so conclusions from the study of the electron: cathode rays have identical properties regardless of the element used to produce them. So interestingly enough, all these rays that came out produced the same kind of particle. Now we know it's electrons, and so all these particles that we saw were actually just electrons, and they were all the same. Atoms are neutral, so there must be a positive particle in the atom to balance the negative charge. And that's where J.J. Thomson got his plum pudding model. Since it was always neutral, if there was electrons coming out, there must be some positive charge in there. Now we know, of course, those are protons. And of course, electrons have so little mass that atoms must contain other particles that account for most of the mass. And we're going to talk about another experiment that proves where that mass comes from. And before that was able to be discovered, we had to do some use of knowledge from radioactivity. And radioactivity, by definition, is the spontaneous emission of radiation by an atom. And it was first observed by a guy named Henri Becquerel. Turns out that he left a rock that was radioactive, left it on top of, at least this is how the story goes, on top of some photographic film. And when he looked at the photographic film later on, there was all these dots on it. And it was because the radioactivity was actually shooting it onto the film. And it looked at the shape, he saw the shape of the rock, was able to be fascinated by it, and he was using photographic film to actually detect all this radiation that we learned from. And luckily he had the help of Marie and Pierre Curie, husband and wife, who were able to then, were graduate students of his that actually studied and really took all the data of what we know about radioactivity. So there's three types of radiation that were discovered by Ernest Rutherford. First is the alpha particle, and this is something we need to know. Alpha particles are fast-moving helium nuclei. Beta particles are fast-moving electrons, and gamma rays are highly energetic electromagnetic radiation. Now, if you don't know what this is right now, we will go over what electromagnetic radiation is in great detail in the third lesson of this unit. And so you need to know alpha particles are helium nuclei, beta particles are fast-moving electrons, and gamma rays are highly energetic electromagnetic radiation. And whenever you have a radioactive substance, it turns out, using a photographic plate, that if you put the beam through a charged plate, you'll have, of course, a particle that bends upward, and those, of course, what could be attracted to the positive? Well, it's the beta, because those guys are electrons. Electrons are attracted to them. And you'll notice it even travels further up. Because they are so light, they deflect more than the alpha, because alphas are helium nuclei, which are heavier. They don't deflect as much. And then the gamma rays, of course, don't deflect at all, because electromagnetic radiation is neutral, very much neutral. So Rutherford then used all his radioactivity ideas to then come up with a gold foil experiment. And what he did was he flattened out a gold foil as thin as he possibly could. and he took an alpha particle emitter. And you know, this is like just from a perspective, you're taking a golf ball or a baseball and deciding to throw it against the wall, because the gold foil represented the wall. And what turned out to happen was most of those particles went through the gold foil, which meant that whatever structure of atoms we had inside really kind of told them that maybe, because 99% of them went through, that the particles were fired, of course, we talked about that, and then we have the screen on the other side. And so just kind of getting an idea, if you actually, so let's say you don't even know what you're hitting, and you get this situation where it shoots up and shoots down from these beams, whatever this hits is probably making it bounce downward, whatever this is making it bounce downward. You can get a sense of what the shape is inside. And so if you look at the one on the right, you see that 1 goes through, 2 deflects upward, 3 kind of comes back, 4 deflects down, and 5 goes through. When we remove these pictures, a triangle definitely would be a shape for this one that matches, and this one may be a sphere that kind of matches this one. And this was kind of the pattern that they saw for most of the deflections. And so here's what his findings was. Most of the particles passed right through, which meant that whatever it was trying to hit was empty space. A few particles were deflected, which means whatever it hit kind of deflected also like a sphere, like in that second picture. And very few were actually greatly deflected. So that meant that, and of course this puzzled him, because this whole idea that not going to the gold foil was like him trying to shoot howitzer shells. Of course, this is around the time of World War I, bouncing off tissue paper, which made no sense to him. And so his conclusion is that there was something inside the atom that was very small, and he called that the nucleus. And the nucleus also must be very dense, since most of the space was empty space. And the nucleus must also be positively charged. So when we talk about the size of the nucleus in relation to an athletic stadium, what we're talking about is like the size of a ball bearing, and that ball bearing, of course, would be the nucleus, and the whole stadium would be considered empty space. And of course, that gives us a picture of how much empty space would be. It's like us taking a ball bearing or a golf ball, stick it in on the 50-yard line in our stadium. That's the nucleus, and the rest of the whole stadium is empty space. And from all of this work, we know now some information. The electron has a -1 charge, has a mass of 9.109 times 10 to the -31 kilograms. Its location outside of the nucleus. The proton has a +1 charge, has a mass of 1.673 times 10 to the -27, and its locations in the nucleus. Later on, we discovered that the neutron was also discovered in the nucleus, and its mass is roughly the same as also of the proton, just a little bit heavier. So, in terms of atomic scale, this of course is the size of the atom. The nucleus is like 1/10,000th the size of the atom. A proton is 1/100,000th times the size of the atom. And the quark that's inside the proton is 1/100,000,000th the size of that. And the electron, at its largest, is roughly the same size as the quark. And so those guys are really, really small. And of course, for the AP exam, we don't study quarks, but I just want to give you some perspective. So again, as a review, most of the mass of the atom is in the nucleus, protons and neutrons. Electrons are found outside of the nucleus in the electron cloud. And of course, most of the volume of the atom is empty space. So you need to kind of have this picture that a lot of it's empty space, very small nucleus. And on a side note about quarks, protons and neutrons are not fundamental particles. It turns out that a neutron and a proton both have quarks. Protons in typical have 2 up and 1 down quark, and neutrons have 2 down and 1 up quark. Electron is a fundamental particle, but protons and neutrons are not. Again, not as important to the AP exam, but it's just one of those pieces of information that you might want to know if you're ever on some trivia game. Okay? So if you have any questions, come see me. I apologize, this is a very long video, but I just want to make sure I cover some fundamental concepts, some history. It's good to know the history. It's good to kind of be aware of it because they do ask questions about it. You got to know what J.J. Thomson did. You have to know how Dalton had an atomic theory and how some parts of it are incorrect. And you also need to know, the experiments of the Millikan experiment, the experiments of Rutherford, and make sure you understand how those contributed to the atomic structure and picture. Okay, that's all for today. If you have any questions, come see me. We'll talk to you guys later.